There are lots and lots and lots of formulas for pi. Go to Wikipedia, Google formulas for pi, and there is a ton of them. Here I'm going to give you two and show you how one derives them. There are lots of formulas for pi in terms of what we call infinite series, infinite sums, but some of them, although they do work, they add up to pi, the convergence is slow. What that means is that I need to add lots of terms in this one, for example, to get close to the value of pi. That's why we create other formulas. From this one, we are going to generate this other formula that converges a lot quicker. This sum is 4 times the alternating sum of 1 over odd numbers, and that one converges pretty slow. And this one is 2 times the infinite sum of, I'll talk about double factorials in a second, but what you need to know is that this term over here converges to 0 slowly, but it goes to 0, times 1 over 2 to the n, which goes to 0 very quickly. So this goes to 0 very quickly, and that means that this thing is going to converge to pi pretty quickly. A double factorial is 2n double factorial is the product of all the even numbers between 2n and 2, and 2n plus 1 factorial is the product of all the odd numbers between 2n plus 1 all the way up to 3 times 1. That sum is equal to 4 times 1 minus a third plus a fifth, etc., while this one starts like 2 times 1 plus this quantity plus that quantity, etc. Let me give you some data about the convergence. When n is 10, the first approximation is 3.23, so not too bad, but it's not close enough to pi. The second approximation is already at 3.1411. When we do 100 terms, the first approximation is still at 3.15, so not even that digit is not correct, while the second approximation is 3.141592653558, all the way up to here. That is correct. That should be a 9. So that second approximation is pretty awesome. How do we come up with such formulas? We use Taylor series. The arctangent of 1 is pi over 4, and the Taylor series for arctangent of x is given by this Taylor series. So at 1, it does converge. So if I plug in 1 here, I'm going to get pi over 4, and this is the first formula we used. For the second expression, we use what we call the Euler transform. So if you have a function that is given by a power series, then this expression is what we call the Euler transform of the function f. And if we know the power series, then this expression has this expression as a power series in x. And then a combinatorial argument tells me that this here is actually the quotient of double factorials that appears in my formula. Moreover, if I plug in x equals a half in this formula, here I get a 2, and here I get a 1, so I get f of 1, but f of 1 is the arctangent, so this would be pi over 4 times 2. So that's pi over 4 times 2, and if I plug in a half on the right-hand side of the expression, then I get the infinite sum that I wanted, and if I solve for pi in there, then I'm going to get the formula for pi that I was looking for.